All right, a repeated measures ANOVA is used when you have time series data with more than 2 time periods. In a one-way repeated measures design, each subject or case in the study is exposed to all levels of a qualitative categorical variable and measured on a quantitative variable during each exposure. The nominal variable is referred to as a repeated measures factor or within subjects factor, and it can just be time period. The quantitative variable is called the dependent variable. Often in a one-way repeated measures design, the levels of a within subject factor represent multiple observations on a scale over time or under different conditions. For example, there was a cursing experiment where subjects were asked to plunge their hand into a bucket of ice water, and they were timed to see how long they could stand it. The first time they were allowed to curse, and the second time they were not allowed to curse. And so they were comparing the pre and post times under 2 different conditions. And of course, the cursing allowed them to keep their hands in the bucket of water longer. Sometimes the level of within subject factor may represent scores from different scales, and the focus may be on evaluating differences in means among these scales. But in such a setting, the scales must be commensurable for the ANOVA significance test to be meaningful. So what that means is that the scales must measure individuals on a same metric, and the difference scores between the scales must be interpretable. Post hoc tests are appropriate when you want to know the difference between all pairwise comparisons or you don't have a specific hypothesis about where the differences will lie. These comparisons may be evaluated by using a Bonferroni post hoc test. There are other post hoc tests. Later we'll use a Tukey test. Contrasts are used when you have hypotheses about differences between specific levels. These can get really complex, but we will do the simple one. All right, so let's look at a scenario of a longitudinal study. Janice is interested in determining whether the average man wants to express his worries to his wife more or less the longer they are married. Janice develops the desire to express worry scale. She has men take the DEW when they initially get married and then at their 5th, 10th, and 15th wedding anniversaries. She decides to conduct a one-way within subjects ANOVA that involves only those 30 men who made it to their 15th wedding anniversary. The within subjects factor is time with 4 levels, 0, 5, 10, and 15 years of marriage. And the dependent variable is the DEW scores at the 4 time periods. Janice's SPSS data file has 30 cases and 4 variables. The 4 variables are the initial DEW score and the DEW scores after 5, 10, and 15 years of marriage. So the first assumption we have to do to consider is that you have one dependent variable, which is measured at the continuous level. That is, it's measured at the interval or ratio level. The second assumption is that you have one within subjects factor that consists of 3 or more categorical levels. A factor is another name for an independent variable, often referred to as the within subjects factor. The within subjects part simply means that the same cases or participants are either measured on the same dependent variable at the same time points or are measured on the same dependent variable while undergoing the same conditions known as treatments. A within subjects factor has categorical levels, which means that it is measured on a nominal or ordinal scale. Such ordinal variables in a one-way repeated measures ANOVA are typically 3 or more time points. For example, 3 time points where the dependent variable is measured: pre-intervention, post-intervention, and a 6-month follow-up, for example. The one we're going through right now has 4 time periods. Okay, assumptions 3, 4, and 5. 3, there should be no significant outliers in 3 or more levels of the within subjects factor. 4, the distribution of the dependent variable in the 3 or more levels of the within subjects factor should be approximately normally distributed. And 5, the variances of the differences between all combinations of levels of the within subject factor must be equal. This is known as the assumption of sphericity. These are all going to be tested by SPSS. So our null hypothesis is that all population means are equal, just like in a regular ANOVA, where the mu is the population mean and k is the number of levels of the within subjects factor. For ours, we have 4 levels. Or the population means at the different time points are equal. So the population mean pre-intervention, mid-intervention, and post-intervention are all the same. And the alternate is that at least one population mean is different. Therefore, they're not all equal. So study design 1. You can determine if there are differences between 3 or more time points. If you have a study design where you're measuring how a dependent variable changes over time in the same participants and you want to compare 3 or more time points, the trend, you would do study design 1. If you want to look at the differences between 3 or more conditions or treatments, you would have a study design where the same participants are being measured on the same DV but under 3 or more conditions. All right, here's a screenshot from SPSS. This is how you would input your data. Here, the only independent variable is time period or condition at each time period, and we have 4 separate columns for each. The measures are the same, though. The measure is the same at each time period, not different measures, meaning this could be weight at different time periods or grades on a test, but not math versus English test unless those are on the same scale, or you couldn't do weight versus height. In a one-way repeated measures ANOVA, we only have the time or condition variable as an independent variable. Later in this PowerPoint, we'll add another IV and a two-way repeated measures analysis of variance. Using the Analyze Explore, we're going to move all our variables into the dependent list and click Plots and select Normal Probability Plots with Tests. You can uncheck Stem and Leaf. I had left this checked, but you can uncheck that. And we can see that we have normal data. Everything is here, non-significant. So what if it is significant? Then run the test regardless, because one-way repeated measures ANOVA is fairly robust to deviations from normality. So you can say that and just add a citation. So we say in APA, DEW scores are normally distributed at each time period as assessed by the Shapiro-Wilks test. P is greater than 0.05. All right, and then we're going to test for outliers. So I've ran box plots, and those just come with the Explore routine. And you can see that in time 2, in time 3, and in time 4, I have outliers. So if they aren't a data entry, the error, then we violate the assumption of outliers. All right, so if you've established that an outlier is neither the result of a data entry error or measurement error, it's most likely a genuinely unusual data point. It is these genuine data points that are hardest to deal with because although they're not ideal from a statistical perspective, they violate one of the assumptions of the one-way repeated measures ANOVA. There's no good reason to reject them as invalid. Unfortunately, what to do in this situation is controversial and there's no single recommended procedure. If your outliers are legitimate data points, then you can make decisions based on previous research and cite it. For now, we're just going to keep them and move on. So you go to Analyze General Linear Model, Repeated Measures. In the Within Subjects box, you see this factor. You're going to type in time, and you're going to specify that there are 4 time periods. We're going to name the variable, the measure name, DEW, click Add, brings it over, and you can see it here, and then we click Define. First, we're going to do the analysis with the post hoc test, if you're not sure where the differences are, and then I'll rerun it with contrasts. So you move all of these over. You can either highlight them all at the same time by holding Shift and clicking the arrow, which will bring it over and label these, or you can do them one at a time. Then we're going to click Estimated Marginal Means, which brings this up, and we're going to click Time, bring time over, rather, and click Compare Main Effects and select Bonferroni, then we'll click Continue. In Plots, we'll click Plots next. We're going to move time over, and then we're going to click Add, and then we're going to click Continue, and then we're going to come over here and click Options, and we're going to say Descriptive Statistics and Estimates of Effect Size. If you want contrasts, if you want to compare each to the reference category, choose Contrast up here. Click Contrast and you get Polynomial. Click Simple, right? We want to make it simple. We come down here and click Simple from the drop down. And if you want time 1 to be the reference category, click First right here, and then click Continue, and then OK. So the first thing we get is just it tells you that the within subjects factors are in your model. Here are the means and standard deviations for each of the time periods. You can see that the means decreased as time went on, but the results also became more variable because the standard deviation went up. This multivariate test is a different approach to doing this. This one assumes independence of observations and multivariate normality and doesn't assume sphericity. So when sphericity is assumed, some say the approach is more powerful. If you do use the multivariate approach, Wilks lambda is the most common, and you would report it out like that. But we're just going to stick with the univariate approach. Assumption of sphericity is that the differences between the level of the within subjects factor, i.e. time, have equal variances. So this Mauchly's test of sphericity, we come over here and we look, and we say that if it is statistically significant, you violated this assumption of sphericity. Increases the type 1 errors. Alternatively, if the test is not significant, you have met the assumption. Here we don't have sphericity, but we'll stick with the univariate test. And you just reported out chi-square of 5 degrees of freedom here is equal to 20.2, p is equal to 0.001. Since we don't have sphericity, we need to look at the greenhouse Geiser correction, or epsilon, values in the red rectangle. So the rule of thumb is that if it's less than 0.75, we'll use the GG test. If it's more than 0.75, this one, then we would use the Huyn-Felt. But here we're going to stick with the GG because it's less. So we'd say Mauchly's test of sphericity indicated that the assumption of sphericity had been violated and reported out. And here's a citation for that. So if we had sphericity assumed, we'd use this top row for the numerator and denominator, but we don't, so we're going to use this greenhouse Geiser, and we would write it up. DEW scores were statistically significantly different at the different time points. F of 2.09, 60.7 is equal to 7.66. P is less than 0.01. All right, if you want contrast, here's where we see if we are significantly different than the reference group. So it looks like later in the marriage, the men are significantly less likely to discuss their worries, right? So we have time, level 2 versus level 1, it's not significant. Level 3 versus level 1, it is significant. And level 4 versus level 1 is significant. But we can't check 2 and 3 and 2 and 4, or 3 and 4 with contrasts. We will when we look at the pairwise. This test of between subjects effect, we don't have between subjects right now, so we can just, this is like a null model because it's just the intercept, we can ignore that. And then we already got these descriptive statistics, so we can just kind of move on. Now, if you want the post hoc, now we see we have 1 is different than 3, 1 is different than 4, which we already saw with the contrast, but now we can say 2 is different than 3, and 2 is different than 4. But 3 is not different than 4, right? So reporting how post hoc tests, you need the means and standard deviations from descriptives. Typically, you don't have to do it this way. You can just tell me what the time periods are like here. So watch, there was a statistically significant difference in DEW scores between time 1, those are the means and standard deviations, and time 3, and time 1 and time 4, time 2 and time 3, and time 2 and time 4, but not between time 3 and time 4. You can just write it out like that. If you want contrast, you would say reporting contrast is the same as post hoc, but they're in reference to time 1. We won't get the highlighted comparison below. You still need the means and standard deviations from descriptives. So you can't say that the between 2 and 3, 2 and 4, but not 3 and 4. You can't say that with the contrasts. So let's graph our results, something that we haven't done before. Go into Chart Builder and select line. So we select line. We bring this one over, just drag it up here, and select all the time periods by holding down Shift and drag to the y-axis. So I would hold down Shift, drag these all to the y-axis, and then you get this box pops up and you click OK. All right, so then the first thing you do is click Display Error Bars, and then you would click y-axis, and then click, because the DV is continuous, you want to change the scale, otherwise that y-axis won't show the true scale. So here, 1, you want to uncheck this like this minimum right here, and it'll say custom 0, and you can just leave it like that. You can scroll down here and change the title and footnotes and such as you wish. Click OK, and we get, it's not very exciting, but we get a graph. If there was more variability, it might be more interesting to look at. Okay, so let's look at our results. A one-way repeated measures ANOVA was conducted to determine whether there was a statistically significant difference in DEW scores at 0, 5, and 10 and 15 years of marriage. The data was normally distributed at each time point as assessed by box plot and Shapiro-Wilk test, respectively. There were outliers which were left in the calculation. The assumption of sphericity was not met as assessed by Mauchly's test of sphericity. DEW scores were statistically significantly different at the different time points. That's the omnibus test. Examine and contrast we see, and you have to go back and report that. Just tell me which groups were significantly different. Right, a two-way mixed ANOVA. is used when you want to compare the mean differences between groups that have been split on two independent variables. The primary purpose of a two-way mixed ANOVA is to understand if there is an interaction between the two independent variables on the dependent variable, and is often used to determine whether there are differences between independent groups over time. A two-way mixed ANOVA has one between subjects factor and one within subjects factor. The between subjects factor has independent groups, like I just said, and the within subject factor has related groups, also known as repeated measures, such as time or pre and post intervention. A primary purpose of carrying out a two-way mixed ANOVA is to understand if there was a two-way interaction, i.e. an interaction between the between subjects and the within subjects factor. This ascertains whether the effect of one of the factors is dependent on the value of the other factor. So a two-way mixed ANOVA is also often used when you have undertaken a study where you have measured a dependent variable over time in two or more different categories, and you want to know whether the dependent variable responded differently over time in these categories. More generally, a two-way mixed ANOVA can be run when you have measured one between subjects factor and one within subjects factor, and want to understand if there's an interaction between these two factors on a dependent variable. The requirements to do a repeated measures analysis of variance is that you have a ratio scale dependent variable and that you have two levels of a categorical variable. This is called the between subjects factor, and the within subjects factor is time. So at least two levels. You can have more than two. So when you look at mixed ANOVAs, you need to consider the interaction term first. In the scenario I'm about to show you, we have three time periods, pre, mid, and post, and three groups. So we have control, intervention 1, and intervention 2. So we have 9 cells, which is a 3x3 design. If the levels of the groups change consistently over time like this, we don't have a significant interaction. But if they do change over time, depending on what group you're in and what time period you're in, then you have a significant interaction. So like I say here, this shows the top group consistently did better, and this one is kind of inconclusive because there's a significant interaction. So the scenario is a researcher was interested in discovering whether the intensity of an exercise training program, but with equal calorific expenditure, had an effect on cholesterol concentration over a 6-month period. To answer this, they implemented 3 different interventions. In one intervention, the participants did not change their current sedentary lifestyle. This was the control intervention. In another group, participants underwent a low-intensity exercise training program that expended 1,000 kilocalories per week. A final group underwent a high-intensity exercise training program that also expended 1,000 kilocalories per week, but therefore exercised for less total time. The participants in each intervention were different, and all interventions lasted 6 months. Cholesterol concentration was measured 3 times, at the beginning, mid, and at the end of the interventions. Participants' cholesterol concentration was recorded in the variable pre for pre-intervention, mid for midway, and post for post-intervention. These 3 variables make up the within subjects factor, time, and the scores within these 3 variables reflect the dependent variable, cholesterol. The different interventions were represented by the variable group. In the variable terms, the researcher wants to know if there is an interaction between group and time on cholesterol. So we have assumptions. You have a continuous dependent variable. You have one between subjects factor, and that is categorical with 2 or more categories. You have one within subjects factor, which is the independent variable that is categorical with 2 or more categories. This could be just the time period. There should be no significant outliers in any cell of the design. The dependent variable should be approximately normally distributed in every cell of the design. There should be homogeneity of variances, and there is homogeneity of covariances, which is the multi-sample sphericity. So first, you run the explore procedure. You put your different levels of the within subjects factor in the dependent list and click plots. We're going to do normality plots with tests. We can see that we have no significance, so we have normality. We don't have any outliers. Now we're going to run the procedure. Analyze general linear model, repeated measures. The within subjects factor is time with 3 levels. The measure name is cholesterol, so I've moved those over. I've got cholesterol and time, pre, mid, and post. and then we're going to click plots. So I want to put groups on the separate lines and time on the horizontal axis. I click add. It gives us the interaction term. Then we're going to go to continue and click estimated marginal means. I'm going to bring group, time, and group interacting with time and do compare main effects and compare simple main effects and click Bonferroni. Then I'm going to click continue and go to post hoc. I'm just going to bring post hoc test over for group, and we're going to look at Tukey, which is just a different type of, it's Bonferroni. Tukey is a little bit more generous in terms of finding significance than Bonferroni. So we click continue, and then we're going to look at studentized residuals. Those are save. Then we're going to click options, and we're going to do descriptive statistics, estimates of effect size, and homogeneity test. It's kind of backwards, but you can't check the assumptions for all the cells until you have run the ANOVA, so we'll get tons of output, but we'll keep going and we'll go back and evaluate our output. So we say continue and OK. So I want to just look, we get these studentized residuals for each of the time periods. I'm just going to go in and do descriptives and look at the maximum and minimum, and I can see I don't have any beyond plus or minus 3, so we're good. We don't have outliers. We're going to do the same thing. We're going to go to analyze descriptive statistics and do some quantile plots and do SR, our studentized residuals for the 3 time periods. We're just going to move them over and click OK. We can see close enough. We're going to say they're normal enough, and know that mixed ANOVAs are fairly robust, 2 deviations from normality. Then we look at our Levines and our boxes tests. We can see all of the different Levines and the different levels of the time periods are fine. And we look at our box and we see not significant, so we're good. Now we'll go back and we'll look at sphericity. We have sphericity because it's not significant. And so we want to look first at our interaction term, and we see that we have a significant interaction. So we have a significant interaction effect. There was a statistically significant interaction between the intervention and time and cholesterol concentration, and I would write it 84, so 4, and then the error term 84 is equal to 107. That's a very large F statistic. P is less than 0.0005, partial eta squared 0.837. When your interaction is significant, you stop there. You can't really evaluate main effects because they aren't consistent because there was an interaction. We'll look at multiple comparisons really quickly. There's a difference between the control and the second intervention, but we see there's a significant difference between the control group and the high-intensity exercise group, but not between the control group and the low-intensity exercise group. All right, looking at the profile plots, we can see that the first intervention and the second intervention started at a similar place, but here's where our significant interaction occurs. It crosses over the control group. Everybody on the calorie diet had a decrease in their cholesterol, but those who added the high intensity exercise had the most significant. So to write it up, we say there were no outliers as assessed by box plot. The data were normally distributed as assessed by Shapiro-Wilks. There was homogeneity of variances and covariances assessed by Levines and boxes, M-test respectively. Mauchly said we had sphericity. There was a statistically significant interaction between the intervention and time and cholesterol concentration. Cholesterol concentration was statistically significantly greater in the control and low-intensity exercise group compared to the high-intensity exercise group. Cholesterol concentration in the low-intensity exercise group was not statistically significantly lower than the control group. Okay.